Hello, welcome back to the course on audio signal processing for music applications. In this programming class of the third week of the course, I want to introduce the actual code that is within the SMS Tools package that implements analysis and synthesis using the DFT. In particular, what we're going to show is the dftModel function that from a fragment of a sound, x of n, performs the FFT algorithm and then generates a magnitude and phase spectrum, and then that can go into the inverse FFT and it returns another fragment of a sound that hopefully it should be identical to the input sound. Okay, so let's go to the editor, and let's show the dftModel.py file that is within the models subdirectory of the SMS Tools package. Okay, in this file you will find three function definitions. The first one is called dftModel, and this is one that implements the whole analysis and synthesis. So the input is the input sound, x, the window that we're going to multiply by, and the FFT size capital N, and it will return the output sound, y. Okay, and then many times we just need the analysis part or the synthesis part. So in this file we also find just the analysis. So from the same input x, the window w, and capital N, it returns the magnitude and phase spectrum. And the DFT synthesis, the function that implements the synthesis part, has as input the magnitude and phase spectrum and the size of the sound to be generated, of the windowed sound, and it will return y, which is our output signal. Okay, and within that, basically, it has the code that we talked about in the previous programming class, in which we just have to window the signal and put the signal in a way that is centered around zero, what we call zero phase windowing. So for example, well, let's look at the dftAnal function, which is very much like we showed in last class. So this beginning is declaration and creation of some variables. Then we have the window that we input and we normalize it. Then we window the actual signal. Then we have this buffer, and we're centering the windowed signal in the buffer at 0. Then we compute the FFT, and then we will generate the magnitude and phase values by taking the log for the magnitude and unwrapping the phases, so that we get a nice looking resulting spectra. And in the synthesis, it basically does the inverse. So again, we have to declare all these variables, and then we have to initialize the output sound. And a major difference is that the input, the magnitude and phase spectra, are only half of the values. Since the spectra are symmetric, the dftAnal function only returns the positive frequencies. Therefore, in the synthesis, we have to recompute the negative frequencies from the positive ones. And of course, since our symmetric is very simple, the positive frequencies are just direct. So getting the magnitude and phases, we just convert to rectangular to complex numbers. So by using this kind of Euler's formula. And then for the negative frequencies, we just get those, but reading it in a reverse way, so that we get the symmetry aspect of it. And of course, the phase, we negate it so that we get negation of the phases. and that's it. Then we obtain the inverse Fourier transform by calling the IFFT function that gives as input the complex spectrum. Then we just get the real part, because we want the real signal out of that, and then we have to undo this zero phase, this centering around zero, so that we get back the signal as we had it originally. Okay, so you can look at these with more detail, both the synthesis and the analysis functions. I think they're quite well explained here, so you can have a grasp of them. But in order to test them, I created a small program, okay, in which I get all these packages. I specify the directory where these models are, both the utility functions that I'm going to use and the DFT model. Okay, so from the current directory, I have to specify this relative path to the models directory so that it finds these two packages, the util functions and the DFT models package. Okay, and now we can start reading a file. So I read a piano sound file, also relative to this current directory. That's where the sounds are, and I use this function that I already have been using to return an array of floating point values. Then I use a function that generates the windows. Okay, get window allows us to generate smoothing windows, and we'll talk more about it next week. In this particular case, the Hamming window of a given size, 511, and it returns an array of these values. Okay, then we need to get the fragment within the input array that I'm going to analyze. So I start at second 0.2, and then I have to convert to samples. So I multiply to the sampling rate, and I get the samples of X that start at second 0.2, and that lasts for m samples. And now we are ready to compute the DFT of that. So I call the DFT anal function from that module that we just saw. The package, we name it DFT. So we call the DFT anal, and I pass it the fragment of the sound, the window that I want to use, and the size of the FFT, which I gave the number 1024. And then I can send the output values to the DFT synth and get back the synthesized sound. It has to be normalized by the window. There is a whole bunch of normalization factors that have to be used, and sometimes are not so intuitive, but anyway, you can check it and you can make sure that you need this normalization factor. Okay, so now from the terminal, I am in the workspace, and I have this file, the test4 there. So I can start IPython with the pylab command, so that I get the matplotlib package into that, and I can run the test4. Okay, that executes that. So let's check that we did things right. So for example, let's plot the X, which is going to be our input signal. Okay, that's the whole piano signal, a little bit long, more than close to 17,000 samples. No, 170,000 samples. Okay, we can plot just the fragment that we chose, X1. Okay, this is just a fragment of starting at 0.2. We can also plot the smoothing window that we applied. So we can plot W. This is our window that we're going to multiply by the signal. Okay, and then out of the DFT anal, of course, we can plot MX, which is going to be the spectrum. Okay, so this is the positive side of the spectrum, going from 0 to half of the sampling rate or half of the FFT size. So in this case, it's 512. Okay, and of course, we can also plot the phase spectrum, EX, and that's the phase unwrapped phase spectrum that we have. Okay, so that's basically the whole thing that we want to show. And then there is another file in the models interface directory that is the one that basically integrates the analysis synthesis and makes nice plots, and in fact is the one that is being called by the interface that we are showing in the demo classes. So this is the dftModel function file that, again, it imports all these packages the same way that we did, and then it has one single function, a main, that has a pre-defined variables that, of course, they can be changed and that we can compute, and then it does the computing as we have done now, and then it plots several figures with correct plotting axes and labels, etc., etc. So I copied this file into the workspace, so I have it as a dftModel function. So if I run this, it will execute the default parameters and it will compute and plot this. Okay, so this is the result of this analysis synthesis of a fragment of the piano, and here now it shows in a nice way, well, with the labels, the time in seconds, the frequency in hertz, and the amplitude explained in decibels, the phase again, and then the output signal, which is the windowed version of the input signal. And of course, as we showed in another class, we can zoom in into fragments of these to visualize certain aspect of that, so we can understand some particular harmonic, how it behaves. Okay, and that's basically what I wanted to show. So let's go back. So we have shown the analysis and synthesis of a sound and the code that implements that in different versions, and so all of this is available in the GitHub directory that you have found here in the SMS tools that you download. You can look at there is quite a bit of information about that and well explained, and of course the sounds that we are using come from Freesound, but of course they are also in within the SMS tools directory, so it's easier to have access to. And that's all. So we have seen how to program the DFT and how to use the actual existing code of the SMS tools to perform the analysis and synthesis, and hopefully this has allowed you to understand better the DFT, and this will be fundamental for understanding the next step, which will be next week, which is going to be the short time Fourier transform. We're going to put together this DFT analysis into an analysis synthesis framework that really works for any sound and that allows us to analyze and synthesize larger sounds, not just small fragments. So this is all for today, and I hope to see you next time. Bye-bye.